Hello folks, we're back with more math. Today we're going to do Lagrange multipliers. So the idea here is if we want to maximize or minimize some function, we want to find its extreme values, but we have some constraints that we have to keep in mind, then we'd like to use this method. So you might remember the silly questions we did in Calc 1, like, given that the sum of two numbers is, let's say, 10, find the largest product they can be or something like that, okay? Or, we used to do questions like, given a fixed circumference, what's the largest area a rectangle could have, or what are the dimensions of the rectangle with the largest area? So those sorts of questions, but with more variables. Basically, that's the idea. We have some constraints we have to keep in mind. Without the constraints, we already know how to maximize and minimize functions. So I thought we'd see these constraints in action with a similar question to what we had in Calc 1. So here's the type of question we'd like to be able to do. We want to find three real numbers summing up to 9, and the sum of the squares is smallest. Okay, so the numbers x, y, z sum up to 9, but we want to make their squares, the sum of their squares, as small as possible. So in that case, what we're trying to do is we're trying to minimize this sum x squared plus y squared plus z squared if we call the numbers x, y, z. So in other words, we're trying to minimize this function subject to the constraint that x plus y, z, their sum has to be 9. Now, we call the function that we're trying to minimize or maximize the objective function, and we call these constraints, okay? We call this a constraint. There could be more than one constraint. We're gonna see what we do with two constraints and so on. So it's this setup that we want to do now. In the case where if we were trying to do this with just two numbers, right? Without the z, if x plus y was 9 and we were trying to minimize x squared plus y squared, then I can just, throw the x to the other side and say, well, y is equal to 9 minus x, and plug it into here. That's the kind of thing we did in Calc 1. That's called substitution. When you have three variables or more, that's sometimes not feasible, okay? In this example, there are much harder examples where that is just not feasible. You can't do this solve for one of the variables and plug it into the equation business. It becomes really, really hard, okay? So the way we're going to approach these problems is we're going to assume we're not going to do substitution. Substitution just takes too long, or sometimes it's just downright impossible. We're gonna develop this thing called Lagrange multipliers. Now, before we can get to Lagrange multipliers, we're gonna do this theorem, the orthogonal gradient theorem, which by itself is not much good, okay, but it's got a very useful corollary, which is going to lead us to the Lagrange multipliers, and that's going to be very important. So bear with me while we go through this theorem. It's a very, very important theorem. Again, by itself, you won't see what it's good for until we do the corollary. So let's say we have a function, differentiable, nice function, okay, a good function, in some region D, and we have a curve inside that region, okay? So everything is three variables. You can make them two variables, you can make them four variables, as many variables as you want, or as small a small number of variables as you want. Here we're just doing the three-dimensional version of it. So we have a three-dimensional function defined on some domain, okay? And inside domain there's a curve, okay? And we parameterize that curve with respect to time, let's say. And with respect to time, the vector equation of it is r of t is equal to g of ti plus h of tj plus l of tk. This is again my L. You remember my L is kind of funky. And let's say this curve is inside in the interior of this domain. It's inside the domain and it's a smooth curve. It's got continuous derivatives. None of them are zero at the same time. It's a nice curve, okay? So we got a nice function. We got a nice curve. If we want to find the points on P on the curve where the function has local maxima, minima, okay, relative to its other values on C, then gradient of f has to be perpendicular to C at P, okay? So what this says is, you know, you've got some kind of funky curve. I don't know what it looks like, okay? And we have some kind of function, okay? We have some kind of function evaluated on some domain, or including this, okay? So when I plug in the values of this curve, whatever the points here are, into the function, I get some values, right? Okay, whatever these points are, when I plug them into the function, I get some values. So which are the biggest values, which are the smallest values? That's what I'm gonna say. And what we're gonna show, that if, say, this is a maximum or minimum, it's an extrema, what we're gonna say is that the gradient of f is perpendicular. The gradient of f is perpendicular to this. So if you talk about the tangent line to the curve, okay, then the gradient of f is going to be perpendicular to it, orthogonal to it, okay? Orthogonal means perpendicular, basically. Okay, so let's go through the proof of it. It's got a very nice, decent proof. It's not hard. So on C, f takes the values, of course, wherever we see. For x, we're going to plug in g of t. For y, we're going to plug in h of t. And for L, for z, we're going to plug in L of t. So if we want to find the maximum and minimum values on the curve, and because the curve is parameterized with respect to t, we got its equation in terms of t, we want to look at the FDT, right? The FDT has to be 0. So let's look at the FDT by the chain rule. We're going to do df dx and, well, dg dt, okay, chain rule, plus df dy, dh dt, and finally df dz, dl dt. Okay, that's just chain rule. So now I can write this as a dot product of two vectors. Which vectors? Pull the df dy, df dx, df dy, df dz out, and you're left with dg dt, dh dt, dl dt on the side. That's just the derivative of r, right? R was g prime ght, so this is a g prime, h prime, l prime. That's just going to be r prime. In other words, the tangent vector, okay? R prime. So what this is, remember, this was just the definition of the gradient of f times dot r prime of t, the tangent vector to the curve, is df dt. Now, as I said, when we're looking at a maxima or minima, we'd like the FDT to be 0. So that's going to imply gradient of f time the dot product r prime of t is 0. Remember, two vectors give the dot product 0 when they're orthogonal to each other, when they're perpendicular to each other. So that means gradient of f is perpendicular to r prime. In other words, gradient of f is perpendicular to the tangent to the curve, okay? So we conclude, since it's perpendicular to the tangent to the curve, we conclude that gradient of f is orthogonal to c at this point P, where we have an extrema. Okay, so great. So this is something weird. So gradient of f has to be perpendicular to the curve when we have a maximum or minima on the curve. But how am I going to find this point? How is this going to help me out identifying those 2 points? So that's where Lagrange multipliers comes in, okay? So we're going to first do Lagrange multipliers with just one constant, and then we're going to generalize that from there. Let f of xy and g of xyz, two functions of 3 variables, be differentiable, and gradient of g not equal to 0 when g of xyz is equal to 0. So okay, so don't worry about this. I'm gonna say why we need this condition in a second. Basically, this is going to be our constraint function, because remember, g of xyz equals 0. That's just a level curve, right? That's just a level surface, right? It's a level surface. To find the maximum or minimum of f subject to the constraint, this constraint g of xyz equals 0, we need to find values x, y, z, and lambda, okay, such that here is the Lagrange multipliers bit. Gradient of f is equal to lambda gradient of g, and g of xyz equals 0, because that's our constraint. Okay, so this formula you've got to memorize. Okay, now we're going to say why this formula does find the extrema points of f on g equals 0. Why? Because we already saw in the orthogonal gradient theorem that wherever this point P is, okay, on the surface g of xyz equals 0, on the surface g of x, y, 0, that gradient of f is going to be orthogonal, okay, to every single differentiable curve through p on the surface, not on c, sorry, on the surface, on g equals 0. Sorry, there's no c here. Okay, so what I'm trying to say here is the following, think about my hand. I don't have my orange with me, I'm sorry. So let's say this is the surface g, and I'm trying to find f gives values on g. Maybe it gives the, the density. We've seen density of each point. And let's say this is the point with this maximum density, right? This is the point with maximum density. Now, there is a whole, we've seen this with the directional derivatives, right? There is many different curves going through here. There's this curve, there's this curve, there's whatever curve. Now, gradient of f is going to be perpendicular to every single one of them, because each one of them, when they are differentiable, when these curves are differentiable, what if this gradient of f, f takes maximum or minimum values there. So the orthogonal gradient theorem says, well, gradient of f is perpendicular. Okay, so it's coming out like this. Now, also since this is the surface g, right, g equals 0, gradient of g is perpendicular also. Okay, so f sticks out like this, g sticks out like this. Okay, if I turn to you, they stick up both towards you. So that means they are parallel. Or, in other words, since these are vectors, the one is a constant multiple of the other. That's it. Okay, so this lambda, don't let the letter lambda scare you. It's just constant. Okay, you can write c if you want. We usually write lambda for Lagrange lambda. Okay, Lagrange lambda. So it just says gradient of f and gradient of g. They are just basically constant multiples of each other. Okay. So this formula is exactly what Lagrange multiplier says. Okay, it lets us solve these problems. And now we're going to do some examples. So I'm going to go back to our motivation example. Okay, the very first example that we did. Remember, we wanted to maximize the sum of the squares of numbers whose total was 9. Okay, so here we want to maximize x squared plus y squared plus z squared. This is going to be our objective function, okay? And subject to the fact that those numbers have to add up to 9, okay? So remember, in the theorem, because we want a surface and we want a function on that surface, we were going to set them equal to 0, okay? So we were going to set g equal to 0. So I'm going to get my constraint from this equation. The constraint function is going to be x plus yz minus 9. So when I set it equal to 0, it's a surface, okay? So you just set it equal to 0. So now, what does it mean to have gradient of f equal to lambda times gradient of g? Well, gradient of f is, well, that means f sub x, derivative of f with respect to x, has to be some lambda constant times derivative of g with respect to f. Similarly, derivative of f with respect to y is lambda of derivative of g with respect to y, and same thing for f sub z is equal to lambda times g sub z. Now let's get f sub z, well, f sub x, that's 2x, okay? And g sub x, well, that's just 1, okay? So lambda, 1 times lambda, so that means 2x is equal to lambda. That's what I get from the first equation. Derivative of f with respect to y is 2y, okay? And derivative of derivative of g with respect to y is just 1. So lambda times 1, we get lambda. And we get lambda, if c is equal to lambda times g sub z, means, well, 2z, derivative with respect to z, is equal to lambda times 1, okay? So here immediately, because they're all equal to lambda, you see that x, y, z, okay, so we can immediately see that x is equal to y equals to z, okay? Then you can see that they're all lambda equals 2, or you can just simply use this fact, since they're all equal to each other, it means 3x is equal to 9, so x is equal to 3, y is equal to 3, z equals to 3. That's going to give you the minimum sum of the squares, okay? And the minimum sum of the squares is going to be 3 squared, 3 squared, 3 squared, 9, 9, 9. So the total is going to be, f takes the minimum value 27. Now, that's obviously, right, not the minimum value f of x, y, z can take. The minimum value f x, y, z f can take is just 0. You can plug in 0 into everything, and that's 0. This is the minimum value on this plane, okay, on this plane. This is the minimum value on this plane. It's not the minimum value of f, it's the minimum value of f on this plane, okay? So on the constraint curve or constraint surface. Okay, let's do another example. Let's do another example. So here I did a distance example because this got a nice trick to it. We want to find the point on the plane x plus 2y plus 3z equals 13 closest to the point 1, 1, 1, okay? So we want to minimize the distance between this guy and this guy, okay? So we had the formula for finding distance. Now we want to find the point that achieves minimum distance, okay? So in other words, if we take any point x, y, z, the distance to 1, 1, 1 is going to be x minus 1 squared plus y minus 1 squared plus z minus 1 squared square root of it. So we're trying to minimize this distance d. Now, minimizing d is going to be the same thing as minimizing d squared, right? D squared, d is going to be minimum when d squared is minimum. Why am I saying that? Is because if we instead try to minimize d squared, okay, distance is going to be minimized when distance squared is going to be minimized. I don't have to worry about square roots. That's going to make my derivatives a lot simpler, okay? So instead of trying to minimize this function, I'm going to try to minimize its square. F of x, y, z is equal to x minus 1 squared plus y minus 1 squared plus z minus 1 squared. This is my objective function, okay? That's my goal. Subject to the constraint, we have g of x plus yz. G of x, y, z is x plus 2y plus 3z minus 13. Again, I'm just setting the plane equal to 0, okay? Subject to this constraint. Okay, so let's get our formulas straight. So again, we want to use the fact that, sorry, I didn't write it here. Gradient of f is lambda times, not x, lambda times gradient of g, which means their partials are constant multiples of each other, okay? So f sub x is going to be lambda g sub x, f sub y is going to be lambda g sub y, and f sub z is going to be lambda g sub z. So let's take the derivative of f with respect to x. We get 2 times x minus 1. Derivative of the inside is just 1. Okay, derivative of g with respect to x is just 1. So 1 times lambda. So we have 2x minus 1 is equal to lambda. Same thing, derivative of f with respect to y is going to be 2 times y minus 1. And derivative of g with respect to y is just 2. So I'll multiply by lambda. You get 2 lambda. Okay. And derivative of f with respect to z is 2 times z minus 1. And derivative of g with respect to z is just 3. So it's going to be 3 times lambda. Now, when you solve these equations, you get x is equal to lambda over 2 plus 1, y is equal to lambda plus 1, and z is equal to 3 lambda over 2 plus 1. Okay? So plug them back into the original plane. What was our constraint? Our constraint was that these points have to be on the plane, right? So the plane was x plus 2y plus 3z is equal to 13. So straight away plug them in, and we get lambda is equal to 1 after you do the math. So x is going to be lambda is 1, so 1 half plus 1 is going to be 3 halves. Lambda is 1, so y is going to be 1 plus 1 is equal to 2. And lambda is 1, 3 halves plus 1, that's 5 halves. So we get minimum distance when the point is 3 halves to 5 halves on the plane. Okay, so that was a distance example. Whenever you're doing these distance problems, remember, when you're trying to maximize distance or minimize distance, make sure you're actually maximizing the distance squared and minimizing distance squared, because then you get rid of the square roots. It's much easier to deal with. The next, I want to say what happens when we have not just one constraint, but two constraint curves or surfaces. Now this can be generalized. Once you do this, it can be very easily generalized. When we want to find the extreme values of f, x, y, z subject to two constraints, I'll call them g sub 1 equals 0 and g sub 2 equals 0, we need to find the values x, y, z, lambda, and mu. Guys, you don't need to do this mu. If you're having difficulty doing mu's, you can say lambda sub 1, lambda sub 2. It doesn't matter, okay? You can say c1, c2. It doesn't matter. So what happens is, again, if we go back to the orthogonal gradient theorem, well, gradient of f is going to be perpendicular to both of these surfaces at that point. So gradient of f is going to be a constant multiple of lambda constant multiple of gradient of g1, and it's going to be a constant multiple of g2. So gradient of f is going to be a basically linear combination of those. All right, so and of course we want to do g1 is equal to 0, g2 is equal to 0. So this is your equation when you're dealing with two constants, okay? If you were dealing with, two constraints. If you were doing with three constraints, you would do gradient of f is equal to lambda 1 g gradient g1, lambda 2 gradient g2, plus lambda 3 gradient of g3, and so on. You can do as many constraints as you want, but of course they get much harder to solve. And so all the examples we've done have been planes, lines, and all that good stuff. I have a nonlinear example. They've been linear. I have a nonlinear example. It takes a little bit more effort to solve that we're going to see. So what I'm going to do today now is we want to find the extreme value of the function f of x, y, z on the circle formed by the intersection of the plane y minus x equals 0 and the sphere x squared plus y squared plus z squared equals 4. So basically you have the sphere and a plane is cutting it. Of course, when you cut an orange with a knife, right, and you look at the cross section, that's going to be a circle, okay? So we have the circle formed by the intersection of y minus x is equal to 0 and the sphere x plus y squared plus z squared equals 4. We have a circle, and we want to find the extreme values of this function on that circle. Now, one thing you could do is, of course, you can reduce this to one constraint, which I'm not going to do. I want to show Lagrange multipliers in action, because you get y is equal to y minus x equals 0. It implies y minus y equals x. So this is basically going to be x squared plus 2x squared, or in other words, 2x squared plus z squared equals 4. So it turns into an ellipse, okay, if you do it that way. I'm not going to do it that way. I want you guys to see Lagrange multipliers in action. So we want to maximize or minimize f of x, y, z equals xy plus z squared. That's going to be our objective function, subject to the constraints g1 y minus x is equal to 0. Well, it was already equal to 0. Great. And here I have to throw the 4 to the other side. g2 is equal to x plus y squared plus z, x squared plus y squared plus z squared minus 4 is equal to 0. So I have two constraints, constraint 1, constraint 2, and the objective. All right, let's set this guy up. So gradient of f, so we'll have them all here. Gradient of f equals lambda gradient g1 plus mu gradient g2 means, okay, well, let's do it. Let's do the partials. The x partial of f sub x would be there. It'd be just y, right? It'd be just y, and the x partial here would be just minus 1, so you get minus lambda, minus 1 times lambda, and the x partial here would be just 2x, so you get 2x mu, okay? Similarly, let's do the y partial. The y partial is just going to be x, okay? X is equal to, the y partial is going to be 1, so 1 lambda, and the y partial here is going to be 2y mu, okay? And finally, the z partial is going to be 2z for the objective function. It's going to equal to z partial here is 0, so it's just 0 lambda, basically just 0. And the z partial here is going to be 2z, so it's going to be 2z mu, okay? Those are the equations that's got to be satisfied. So from here, okay, so we have three equations. I labeled them 1, 2, 3. Now, it's just basically free for all here, okay? Whatever goes, as long as you can solve these. Some of them, when they are not linear, it's not very easy. Luckily, it's not too hard for this one. I thought about, the easiest one to handle seems like this one, okay? So 2z is equal to 2z mu. So throw this to the other side, you get 2z minus 2z mu is equal to 0. factor out the 2z, you get 1 minus mu is equal to 0. So that means z is equal to 0 or mu is equal to 1. You got two choices there, okay? Z is equal to 0 or mu is equal to 1. Now, if z is equal to 0, from the sphere equation x plus y squared plus z squared, when z is equal to 0, that reduces to x squared plus y squared equals 4. So which means from the plane equation y minus x, because we're going to get y is equal to x, this is going to say 2x squared is equal to 4, okay? And x is equal to plus or squared minus 2 minus the square root 2, and y is equal to plus or minus square root 2. So then the points that we get when z is equal to 0 are which points? Square root 2, 0, or minus square root 2, minus square root 2, 0, okay? Because x and y coordinates have to be equal to 0, and we said this is the case when z is equal to 0. Okay, so we got 2 points from there. We have to try what these guys are doing at the end to see what's going on. Now, when mu is equal to 1, if mu is equal to 1, I go back to these equations. I get, well, y is equal to minus lambda times 2x, and x is equal to lambda plus 2y. Okay, so I wrote those equations, plugged in mu equals 1, and if we add them side by side, if we add them one under another, we're going to get x plus y is going to be equal to 2x plus 2y. The lambdas will cancel, of course. Well, that means we'll throw this to the other side. You get x plus y. From here, of course, you're going to get x plus y. When you throw these guys to the other side, you get x plus y is equal to 0, or in other words, x is equal to minus y. Now, that's a little weird, right? X is equal to minus y is a little weird because the plane was y equals minus x. So from there, I get y is equal to x. So how can it be the case that x is equal to minus y and x is equal to y because of the plane? Well, the only way that's going to happen is when x and y are equal to 0, when they are both equal to 0. Sorry, you didn't see any of that. Oh, sorry, guys. So let me do that again. So y plus x is, so once we plug in mu equals 1, we get y plus x is equal to 2x plus 2y, which is going to give us, the lambdas cancel each other, which is going to give us, throw this to the other side, you get x plus y is equal to 0. In other words, x is equal to minus y. So from there, you can pull out the lambdas, which I did, but you really don't need to, okay? Why? Because we are supposed to be on the plane y minus x equals 0. So from here, you actually get y equals x, okay? So it has to be both the case that x is equal to minus y and x is equal to y. Well, the only way that can happen is if x and y are both 0. So plug that into the sphere, 0, 0, z squared equals 4. So z is equal to plus or minus 2. So we get 2 more points, 0, 0, 2, and 0, 0, minus 2. So to see which one is max, which one is min, okay, we have to plug those in. Plug f of 0, 0, 2 into the equation. What was f? Let's pull f here. Our good old friend f, okay? So f was xy plus z squared. Plug in 0, 0, 2 in there, you just get 4. If you get plug in 0, 0, minus 2, you again get 4, okay? What about when you plug in square root 2, 0? Well, square root 2, that's going to give you 2 times square root 2 times square root 2, that's going to give you 2, plus 0, well, that's just 0, 2, sorry, in total. And minus square root 2 times minus square root 2, that's again going to be 2, plus 0 is again 2. So you get, in both cases, you get f0, 0, 2 is equal to 4, f0, 0, minus 2 is equal to 4, f plus or minus square root 2, 0 is 2, okay, for those 2 points. So this guy is the max, and this guy is the min on the surface, okay, on the surface that we're interested in. You can generalize this to more constraint functions. You can generalize this to more variables. The thing to keep in mind is, of course, when we're doing these examples, we are finding these equations where, well, once we do the gradients, it's not too hard to solve, okay? In real life, they might be terribly hard to solve, okay? When you have nonlinear stuff, you know, it's usually not that much fun to solve them. So you need to get some exercise in solving these equations. Once you set up this gradient of f equals lambda gradient of g business, you need to get some exercise. So again, I'm going to highly suggest that you open up a calculus book and do several of these guys, both with one constraint and multiple constraints, so that you get used to them. All right, folks, that's going to be it. Till next time, take care. Bye-bye.